Hello, sir. Shall we start?
Yes, yes, oh, yes, sir.
Okay. Good evening to all of you. We are today supposed to discuss something related to plotting in the three dimension. At the same time, we were supposed to discuss a few basic things about plotting graphs in graph theory. Of course, we have seen graphs. By graphs in graph theory, we mean something different from graphs using functions. Basically, plotting in SageMath actually means that plotting the graphs of functions, but in graph theory, it's not exactly like that. It's a slightly different thing. So we will try to do some basic graph constructions in graph theory as well. Let us start with the usual plotting, the usual function plotting in three dimensions. In between, we may have to go into some vector related calculus also, because vector calculus mainly deals with some of these functions. Vector fields we have to plot, we are supposed to plot in three dimension as well as two dimension. Let me share the Sage window. So we begin with plotting in three dimension. We have already seen a few commands like plot 3D, which will help us to plot in the three dimension. It is an analogous of a plot function in two dimension. If you use the plot 3D function, you are supposed to provide a function as the argument and ranges of the variable. Remember that when we were plotting in the two dimension, we were actually specifying plot f of x and then the range of x. On the other hand, here we are supposed to provide, because we want to plot in three dimension, we need a function f of xy. Therefore, the z coordinate we are not specifying. Z coordinate we didn't, y coordinate we didn't specify in the plot command in two dimension. Just like that, z coordinate we are not specifying in plot 3D. We will simply mention inside plot 3D a command, a function in terms of x and y and the ranges of x and y. After that, we may define several extra parameters, just as in the case of plot. So remember another thing that as I told you previously itself, the variable x is considered to be an automatic variable in Sage, but y is not. So we need to define the variables. We need to define the variable y before using it. So for the sake of avoiding confusion, we can define this y, x and y both. So let me plot the function f of xy is equal to x square plus y square. Plot 3D. X square plus y square. Now we need to specify the ranges of x and y. X, suppose we take -2 to 2, and similarly y in -2 2. Maybe we can we can just use plot 3D, or we can, if we want to add plots simultaneously together, we may assign this plot 3D the picture plotted to a variable p, and then we can keep on adding other plots to that. Since we are not planning to do that right now, we will just keep this plot 3D command instead of adding all the plots to p, and after showing that the output is here. Looks like a paraboloid, right? Looks like a paraboloid. Same way we can plot any other function like this. Sine x square plus cos y square, or sine. Okay, let it be like this. We are getting something like this, and this is interactive also. You may place the mouse over this picture and you may keep it pressed and you may try to move this to get the three-dimensional visualization. So plot 3D. Now we can add extra parameters as well, as in the case of usual plot, like color. Color equal to red. Opacity equal to 0.5, where opacity is equal to 1 means it's not at all opaque, 0 means not at all visible, only that frame will be there. So 0 to 1, the scaling is 0.1 is the least. Also we can extend along, let us keep it to be 0.6. Aspect ratio also will work here. Here in fact we can give aspect ratio in all the directions. Is a direction, y direction, x direction, y direction is a direction. Suppose we give 1, 0.5, 1, 1, it means that so 1, 1, 1 simply means that give the same kind of aspect ratio in all the directions. X direction, y direction is a direction. 0.5, 1 means that you are reducing it in the x direction. Now you can give figure size also if you want. So figure size, okay, let us see the effect of the figure size in the next plot. In fact, this figure size etc. will work in the case of the usual plot command as well. Figure size is equal to 10. Equal to 2. Fixed size doesn't seem to affect much. You see, 50. Possibly that fixed size is getting affected only if you are saving that file. Figure size 1. What's the implication of this? It doesn't seem to affect this somehow, but as per the documentation, you should actually get figure size, the default one is 4, and if you reduce it further you will be getting a smaller picture, otherwise you will be getting a larger picture. But here these things doesn't seem to affect much. I don't know whether it's because we have taken, okay, let us just take -1, 1. That should not make much difference. So we are getting a sheet like this here. So figure size is 8. So if you use 2, I don't see any difference. I don't know why it's happening like that. It's not very clear to me. Figure size as per the documentation should have given. I don't know whether in your systems it's giving. Yesterday itself we have seen that in my system it was not giving the proper output as expected, but in somebody else's system it was giving the correct thing. So figure size, fixed size doesn't seem to give any impact here, but as per the documentation you should have given. And now you can have one more thing, like let us try to plot one more picture. Plot 3D sine, we just take x square plus y square, x square plus y square. It's a function in the range say, okay, if you do not specify x and y, it will be automatically taken to be the first and second variable. Since we have already defined x and y, we do not have to define it again. Say x minus 3, 3. Even if you do not specify x instead, but just say minus 3, 3, that should work. Minus 3, 3. And some extra coloring options are here, like rainbow coloring option. Let us see the effect of this command. Color equal to rainbow RGB tuple I have already given. Sin x square plus, this is correct, sin x square plus y square, x in minus 3, 3, y in minus 3, 3. So we just change it. Maybe I should use some extra command like, okay, then adaptive equal to true, that a parameter also needs to be enabled. So it's a kind of coloring option. Some extra things are happening here. So, okay, red and using red and blue, it's automatically colored alternatively, but maybe I can use the previous thing then. So if we change it, the numbers, change it further.
Sir, here adaptive equals to true.
Okay, because of this adaptive only, I think this color change will work provided that this parameter is turned true. Okay, let us see. See that adaptive parameter, without that it does not actually work. Adaptive is, yeah, adaptive equal to false is the default thing. So adaptive essentially means that
So true, previously the true was true, t was small.
Sorry?
Previously the adaptive equals to true, that true the t was small.
I think that's not necessary. Both will work, I guess. So let us see. Both seems to work, right?
Okay.
In Sage, both will work. In Python, both will not work. Only that capital T will work. But in Sage, both are working. So it's a color blending kind of option. So it applies some kind of refinement. And one more option we can specify here to get a grid kind of thing. Let us change the opacity. 0.5. Mesh equal to true. Okay, let us just change it to false. Mesh doesn't seem to have much effect. The grid lines are not actually coming. Where are the grid lines? Are we seeing some extra grid lines? Is it because okay, let us just try to suppress this coloring and see if this is working. Let us just change this. Maybe because of the adaptive and some of the options will not go together. Here mesh is false. Now it's working. I think the mesh option probably, I don't know whether we are not seeing it because of the coloring. A mesh option doesn't seem to work along with this adaptive thing, because probably because we are coloring and we are not seeing what exactly is happening behind that. But here you can see that the axis is missing, so we can even add the axis. You can see that it's a kind of frame. So now let us change it. So for that we need to import the axis. We need to import, right? The axis by default it's not going to be there. Okay, let us see if we turn axis to be true, will it work or not? Axis equal to true. Frame, is it frames equal to false? Okay, frame equal to false. Okay, the axis seems to be there, but the axis seems to be really small. So that you can see that the XY axis. Okay, let us turn this mesh also off. The axis is there, but it's really small. Let us try to slightly modify this by getting something else. Let me just modify this appearance by saving this to 1p, p equal to plot. After that I am going to import plot from Sage library. This is necessary. Otherwise axis equal to, axis is not found. From Sage plot, it's a big library, Sage plot, plot 3D, see here by this command we mean from the Sage library. Inside that there is a library called plot. Inside plot there is a library called plot 3D. Inside that again there is a library called plot 3D, and import axis from that. Let us see the effect of this. Let us add an axis to this and see what is this. You can see a bigger axis. Now, what is 1 by 6? So, what is the effect of 1? That's a default axis. Now, we are changing the axis style. 10. Really large. But we are merging this with the axis, so we are not rotating it around the origin, but instead of that we are rotating the entire picture. So axis 10 is really large. Maybe we can remove the colors as well. color equal to black has no effect. Oh, axis is 5. Okay, this axis probably it is getting confused with this. Yeah, now you can see that the previous axis is completely gone. We were modifying the previous axis. Now the axis is here, but I don't know whether it's really easy to see. Axis equal to 5. Is there any option to modify the thickness? There doesn't seem to be any thickness parameter. We just try that. Now you can call for the axis thing, because we have already imported the axis command from Sage library. So the radius, okay, the radius is something that we can give. Radius of the axis as arrows. I think that radius command should probably work, not thickness. Yes, that seems to work. If you go further, it becomes thicker. So we can enable axis, we can remove the frames. If you keep frame also true, you should see both. Frame as well as axis. Now there are some other beautiful coloring options available, which can be taken from something called color maps, library called color maps. Okay, this I will just -3 opacity is already defined, axis is 5, that's already given. So let us change the axis to 3. Okay. Now the color map, I was talking about color map. Color maps. We can see from here that Sage is actually making use of a Python library called matplotlib. Not exactly Python library. Python is also making use of this matplotlib. That's another library. So for getting different types of colorings, we can make use of this color maps. So as I told, in the case of Sage Mathematics, SageMath, the problem is that there are hundreds of options available with many of these commands, but several things are not very well documented. You need to just dig inside that thing. Even you may have to check the code sometimes, because Sage Mathematics, even though it might have started at least I don't know, in 2005 or something like that, but still it is in the beginning stage only, because it's not actually maintained by a team of professionals. But on the other hand, amateur people like mathematicians usually contribute and try to extend the capabilities. So I'm just using an example from the documentation. So let us see the effect of this and try to understand what exactly this is. So color maps is there. Now let me define a plot function once again, a plot 3D function. The same plot probably I will use, or otherwise I will use f of x equal to x square plus y square itself. Plot 3D. A sine function is probably better. X square plus y square within range minus 3 or minus pi minus pi cos y square. So sine x square plus cos y square minus pi minus pi 1 bracket specific. This function already we have seen, right? Now we are going to take something from color map. So let me just add to this. Color equal to, I am giving an ordered pair. So I should have given, okay, variable thing. So color equal to is a parameter in plot 3D. There are several different things that are available. Color maps, I am using HSV. We can of course see the effect of this even before that. Color maps HSV is nothing but it gives a kind of coloring. So that's it. So what type of coloring it will be giving, we need to just look at that. So it creates some, these are some already defined existing coloring styles available. That's it. That's the only thing we can understand, and what type of coloring it gives, we need to just try with that. That's it. Okay, I think here also I need to do something else extra. So let me just define this color. C is, if C is equal to, the C is creating some trouble it seems. So color, this one is creating some trouble. Therefore let me just give x square plus y square. I'm just experimenting with this. Probably I need to take it within 1. I think color, the first parameter needs to be within 1. Therefore, let me just take it to be 0.5 and see if it's working. For C in color 03, color that's still giving the mistake here. So the show. So X ranges, let me just specify explicitly, this is X, this is Y, to see if that's a mistake. No, that's not the mistake. Now let me just come in terms with the documentation by defining C to be a function of X and Y, where C is here, C equal to define CXY. So it seems that it is actually meant for creating a mapping of X and Y and color it accordingly. So for each X and Y, it's going to compute the CXY, and after that only we need to give. After that, the coloring will actually happen. That's what, as per the documentation, it is. So let us define return a float number of x square plus y square instead of what I defined here, and %1 to make it within the range 1. So what are the effects if you divide, if you make it smaller further? Okay, to understand what exactly this is, let us try to see some values of the CXY. 4 CXY. This is nothing but 0. It gives us expected. There is nothing special. But the only thing is that here we are actually looking for in this color command. Okay, let us see the documentation of this plot itself, or color in fact. Okay, that doesn't seem to give much insight, but the only thing is that here we can, the only thing we can understand from this part is that here we are using the C function. This C is actually a function. Now if you use the C function corresponding to x and y, corresponding to each x and y, while plotting, what happens is that the color is getting changed. So but still the color is actually C and color maps. Therefore the first C value, depending upon the first C value, color maps is doing something. That is the only thing we can understand from this, because the documentation of color maps HSV is not very user friendly. If we just ask for the color maps HSV, what it says is that it is some kind of coloring. That's it. HSV. What's going to be HS and V? So this is H, probably SV, linear segment color map. So we can specify CDIT. So it works. That's the only thing we can understand from this. So if we take the documentation and the example from that, we are getting something like this. X square plus y square, x plus y. But this is not the function that I am looking for. Percentage is essentially nothing but it's gives 1. Okay, if you change this function, it will be you will be getting different things, but y square plus y square. Minus 4 4 minus 4 4. Surprisingly, this is not the function as per the definition. Okay, let me just change it once again here. Is it randomly changing? No, there is no difference. So x square plus y square is the function within range minus 4 to 4, and color we are using as C and CM. We are defining this to be x plus y. Okay, maybe I should put this inside. One bracket is probably missing. Maybe I can do like this. After taking the float, let us take it with this. X plus xy by 15 is not giving the exact output as I get in the case of the documentation somehow. I don't know why it's happening like that. Maybe once again, maybe because the CM definition of color maps might have got changed. The definition inside this might have got changed. That's the problem with not very well documented certain systems. So we may have to just depend upon our experience with that system. We may have to just try and error. That's it. There is no other way to understand what exactly is going on. Okay, let me just continue because essentially what I was thinking is that the plotting documentation is giving a picture corresponding to these commands, but the coloring there is not exactly the same as the coloring here. That's what's wondering for me. Probably I am not looking at the correct example. I don't know, or adaptive is true yet. Okay. Oh, sorry. That's my mistake actually. I was checking some example in the documentation that corresponds to some other example. That graph is corresponding to some other example. Okay. So now, just as in the case of this is wrong. So, just as in the case of two-dimensional plotting, as circle we can draw a sphere. For drawing a sphere, we need to simply specify. Okay, let us see. Sphere. So for sphere, we need to specify the center and size. So size corresponds to radius and center at x, y, z. So default is also there. So size equal to 2, we get a sphere. And opacity is possible. Of course, coloring is possible. Mixture of these colors we get. Okay, were we giving color in which way? Okay, in as a list we were giving. What we did here, on the other hand, probably that adaptive is equal to true. We may have to again enable for getting multiple colors. So did we do that there? Yes. So for enabling multiple colors so that it will be distributed in some way, we need to enable this adaptive equal to true. If you do that, then size equal to true, adaptive is equal to true, color is equal to red blue. Probably this this color option is not, color option is available of course. Okay, let us just try to see this once again. So colors, what we are giving is not getting accepted, unexpected end of. Oh, that color command doesn't, color in this way it doesn't seem to work somehow. So that's what I told. It's surprising that some commands, some options are working with the 3D plotting in the plot 3D, but some options are not working as expected in the case of some other three-dimensional constructs. That's basically because of the what do you call, non-standardness in writing the code. So one of the problems with the open source software, I think that's the case, because we exactly copied and pasted the command from there using the color command, but that color command doesn't seem to work with sphere. Such an example we have seen even previously. This seems to work, but if we change it to, if we copy exactly the same thing and paste it here, suppose this doesn't seem to work.
I think actually sphere is inbuilt code, so it is not giving, it is not taking this adaptive.
Yes, that's what I'm saying. So there are different commands available in SageMath for plotting in 3D itself. What we expect is one option available with one particular type of 3D command that should work with the other ones also, right? That's natural logic, the usual logic that we have. But somehow what's happening is these commands are created by different people. This sphere command is created by some person who wrote the code for that. Plot 3D might have been written by someone else, and it might have been code modified as well. So sphere command written by someone else, they didn't consider this color option to be given like this as a list, and adaptive thing also.
If we give the equation of sphere, and then it will may take this adaptive command.
Right. That's what I'm saying. So each and every time what happens is that when we are trying to understand certain things in SageMath, what we may have to do is we may have to just do some trial and error to see if some options are working or not. Okay, that's the only way. So there is no what do you call, exact way of saying whether this thing will work with everything or this thing will not work with everything. We cannot say. Just try and either get a failure or get a success. That's it. So some commands will work. Some of the options will work automatically across different plotting commands, but some of them may not. That's the problem. So the only thing is that if you are encountering such an error, what we can at most do is we just try to remove some of the options and see if it's working. If after removing some options is working, we have to understand that that option is not probably applicable with that particular command. So color equal to red blue type of giving a list of colors is not working with the sphere command. Okay, that's what we understand from this. So we can define cone also like this, but cone we have to import. See, certain things are coming automatically imported, but certain things we have to import extra. So there are certain shapes available in plot 3D. We can just try to see what are the shapes available. Sage plot, plot 3D. From that, let us try to import certain things. So this is not working. Sorry, this is working, but what was that? The sphere one is not working. And color equal to is working, but single color. Okay, from Sage plot 3D. Dot shapes. We may probably see what exactly this is. See that this is a library written by a few authors like this. So basic objects like sphere, box, cone, etc. is provided by this this library. But sphere is a sphere itself. Let us see that the sphere that we previously had starts with small s. This is capital S. So this is a slightly different thing. Maybe some of the things will work with this. Some options are also available here. Like so let us import everything together by the symbol import star. What we mean is import everything in that library. So we will get all the shapes in the sense sphere we get, box we get, cone we get, etc. Remember that using the plot 3D command itself we can construct the sphere, box, cone, etc. But this gives a ready-made package for you to automatically construct the box, cone, etc. without going into defining the function for plotting cone. Right? We need not know what exactly is the function corresponding to the cone for plotting it. In plot 3D you are supposed to give the function name, but if you are using just cone, just box, just sphere, don't worry about that. In the case of box you need to give the dimensions, in the case of sphere you need to give the dimensions, etc. So cone. So from, let us import star, means import everything. Now let us construct a cone. So what is cone now? Now we can ask, because we have imported that. So instead of from Sage plot 3D shapes import cone, we used import star. Import star in the sense that import everything. Star is known as a wildcard argument. So import everything. So if you do this, so we will get actually, so let us take two cones and see. After that we can translate. So what is translation? That also we can try to see. Show, see. So I just used cone for the sake of input. We have to give radius, height, these two are necessary. Radius, height, and color is not really that necessary. Let us just use this. Now the opacity command mostly works with most of the plotting commands. Opacity equal to 0.5. If you give, and if you look at the documentation once again, we were copying and pasting one example from this. So this is it. Now there is a translate also. What is meant by translate? Let us see that translate in action. Let us use the translate with this. Or let us just translate this 0, 0, 0.3. What is happening? Did it go up? Not able to make out. Translation usually means that we are going up. Okay, let us see once again to see what might have happened. So now the base is at which base? Z base is at 1 it seems. Now let us see if you do not translate it. Where is Z base? Z base is at 0. So simply translation, by translation what we mean is just lift it upward. Okay, lift it upward to this point in this direction. So if we ask for lifting in the direction, okay, to understand this properly, maybe we have to add 2 and see the effect. So otherwise we will not be able to understand what the effect is. Let us use the example here. So here one of them is translated and the other one is not translated. Okay, one of them is translated and the other one is not. Let's see the effect of that. So the first one with red is at the origin, the bottom at the origin, and second one, the yellow one, is not at the origin because it is translated without making it slanted here or there. It's translated to 300. Therefore, the x coordinate of its center became 3. So if you want to see exactly if that's the case or not, maybe we can what we can do is we can put a point to make that point clear. C plus equal to point. Was it point 3D? I don't remember. Is it point 3D? I guess. So let us put a point at 300 to understand if that's correct or not. If our understanding is correct or not. There is a point. You can see that there is a point. So the center is moved to this. By translate, what we mean is we are moving the center to this 300. To make it more visible, let's add the opacity as well. You can see that the point is here, 300 is here. So translate essentially means that you move. Okay, you move the cone. You can in fact scale as well. C dot scale. So what will happen if you scale? Scale is actually a common command for all the plots. So if you scale it by say twice, is there any effect? I don't see any effect here. Has it become small? I think it has become. Let's see once again. 0.1. I think the scaling will probably work provided that you have two plots. One is scaled and other is not scaled. Otherwise, you will be seeing exactly the same. Okay, let us try to add one more. One is scaled. So let us add a sphere also. S is equal to, we already have a sphere here. Let us take the sphere. So S plus. Oh, that's become very small. You can see now the effect of scaling is very clear. So suppose that we have scaled it by 0.5. You can see both these things, but both these things are sitting inside. The sphere is having only a radius 2, but these things are appearing inside the sphere. That's scaled. That picture is scaled. If the scaling is by 1, it's appearing perfectly. Okay, that's the effect of scales. So scale, if you are mixing up two plots, probably you can use the option scale. Otherwise, it's not very useful. So if you want to plot a plane, what you have to do is you need to just take fxy is equal to, suppose that we plot a function fxy is equal to 1. What will happen is z equal to 1 will be plotted. Okay, z equal to 1 is actually a plane, and now you need to specify that within what x and y range. Suppose that we want to just plot a plane. Suppose that we want to plot a plane across the center of a sphere. Therefore, the center of the sphere means we are in the radius 2. Right, the sphere is having the radius 2. Therefore, if we plot a plane, suppose we take this to be the sphere, size is 2. Suppose we add to it a plot 3D. Suppose we add to it just one, f of xy is equal to the constant function 1. Suppose we add to it, then we in the range x minus 3, y minus 3, and show. You have a plane here. But remember that this plane is going to be parallel to xy, x-axis and y, parallel to the xy plane. Because we have xy is equal to f of xy is equal to 1, which means that z equal to 1. Right? Using plot 3D, you may not be able to construct a plane parallel to anything else.
For plane, you have written only 1.
Sorry?
For plane, parallel to xy axis, xy plane.
See, ma'am, what we are actually doing is we are plotting the function of f of xy, right? At the place of f of xy, if we specify 1, it essentially means that z equal to 1. If you do not specify f of xy, we simply write 1, it means that f of xy is equal to 1, which is z equal to 1. Z equal to 1 is a plane parallel to xy, right?
Yes.
Am I correct? I think that's the correct interpretation of that fxy is equal to 1, right? Because in the plot thing, we are actually specifying a function in terms of x and y. There is no way to specify it as a function of z and y. We cannot.
Yes.
Now there is probably we can rotate. Let's try to rotate. About. So we need to be a little bit careful. So I am just trying to rotate it. So rotate it in the sense the picture I need to rotate about one particular point in what angle about about what the angle is going to be taken care of. That I need to just think. I'm just trying. Okay, let me just try to rotate. They apply the rotate command. So maybe even after this I can just see that if the rotate is actually working or not. Rotate. Or rotate about the origin. So what is this? What I have given here? What? Suppose we rotate about the 0, 0, 0, and I don't know whether I am rotating it along which axis. I am not very sure about that. I'm just trying. So rotate and show, or maybe I can rotate this and show afterwards. That also doesn't seem to actually work. Maybe can I apply it here? Now once I apply rotate, it's not at all giving any output. Otherwise it is. So maybe I have to use the implicit, but still the rotate command, why is it not working is not very clear. Let me just see. So maybe I can try to rotate as well, and so this is the sphere. I don't know, maybe I can try something like this. This is rotated. About 0, 0, 0. Okay, what happened to this? If this is not there, oh, probably this show is working only with this. Okay, the entire picture needs to be rotated, not just one part of that. That's probably the problem. Okay, let us just try to change this slightly.
Sir, if we rotate sphere, then we can't observe. So if we rotate any plane, then we can.
Yes, I understand. I was expecting, what I was expecting is that to get a plane parallel to the Y is a plane. Say I wanted to rotate that second figure alone, but that's not happening. So the entire picture is getting rotated, not just one part. So because it's a sphere, as you told, we cannot observe what exactly is happening. So we need to rotate a plane itself. So let us try to rotate a plane to see the effect of that, if at least that is working. So this is here. Now just show. So see that this is now a plane parallel to Z axis, but if you rotate it with respect to 0, 0, 0 again, and in the direction say pi by 4, so that we can easily understand if something is happening. But even with respect to what this angle is taken is a little bit confusing. Let us see that. And show is required. So what's happening is the rotation is happening only while showing that. Okay, otherwise it's not happening. Otherwise nothing is happening. Let us see. Now this seems to work. Okay, we can rotate and save. Right, this is what I actually wanted. So constructed the figure here. Now let us remove this. This is not required. So now this plane, but this is now rotated about 0, 0, 0. Oh, rotate about 0, 0, 0 is not working. But what is meant by rotate about 0, 0 then? Rotate. So it's about the vector, I guess. Okay, rotate about the vector 1, 0, 0. So take the vector 1, 0, 0 and form an angle pi by 4 with that vector. That's probably the meaning of it is that only. It's not about the point, but about the vector, it seems. Let us take pi by 2. So 1, 0, 0 is which vector? 1, 0, 0 vector is actually the x vector, right? So the x axis. So rotate about x axis probably. Or otherwise move it to the x-axis to the vector 1, 0, 0 and then rotate. Because this is now at what is x here? X is probably 1, 0, 0. So what about?
Actually, it is perpendicular to x-axis because we have rotated 90 degree.
So if you ask for 0 rotation, what will happen? That we can observe that.
No. No change.
No, but still it's moved. It's not in the center now. Oh, right, because we have already lifted. No, it should have been actually through the center of the sphere because we have taken the plane z equal to 1.
Yes.
But now it is not at z equal to 1. Okay, but it is still at z equal to 1 only, right? Because we are getting z equal to 0 and yes, it is still at z equal to 1. There is no rotation happening. There is no change at all happening. Let us try it. Okay, let me just try to do that once again. So it's here. It looks like this now. Let us change it to 0, 1, 0 and see the effect. There is nothing happening. So 1, 0, 0, there is 0, 1, 0 or 1, 0, 0. If the rotation is not there, nothing is happening. So do not rotate. So I think it's moving to that particular, moving along that vector only if you are applying some rotation. So if you apply pi by 2 rotation, so now it's getting rotated. It's perpendicular to, but 1, 0, 0 or 0, 1, 0 or 0, 0, 1, all these things gives the same result is what? I understand. No, that's not correct. So if you rotate it with 0, 0, 1, rotate with 0, 0, 1, or no rotation, the effect is the same. So what is meant by that then? Is this plane placed to placed along 0, 0, 1 vector and then rotated? Is it moved parallel to 0, 0, 1 vector and then rotated? Is it because of that? I think that's what's happening. This plane is made parallel to the vector 0, 0, 1, and 0, 0, 1 vector is now tangent to the vector probably, or it's normal. I don't know whether it's not parallel. It's parallel or normal. It seems to be parallel now. Okay, 0, 0, 1 is made normal to this vector first of all, normal to this plane first of all. Then it is rotated pi by 2 with respect to that vector. Something like that is happening here. I think that normal, it's taken to be 0, 0, 1 is taken to be the normal vector to the plane. Something similar to that is happening in rotation. So rotation is anyway happening, and we can construct parallel planes like this. At least that much is clear. Okay. Now plot 3D, and apart from that we have seen some shapes as well. Now let us go to something like parametric plotting. Parametric plotting we have already seen in the case of, okay, cylindrical plotting. In cylindrical coordinates also we can plot. So for cylindrical plotting, what we need to specify is we need to transform. So if we define T to be cylindrical, we can plot in spherical coordinates as well. Cylindrical, spherical, both these things are possible. But we need to define the transformation first of all. Okay, let me just see. So once you define the transformation, then using plot 3D itself, you can get the cylindrical picture. So you need to pass certain parameters. So let us try to do with the cylindrical first. After that, we will go to something else. So after that, okay, let us define a transformation first of all. We need to apply a transformation. So the technique is take T is equal to cylindrical. Remember that in cylindrical parameters we usually specify the height. So to locate a point in the cylindrical parameters, we need to specify the radius. We need to specify to mention a point with the radius is required, the height is required, and the angle is required. Three things are required. So we are going to define a cylindrical transformation like this. So the first parameter, we are going to say that that's the height parameter we need to specify. After that, there are two optional parameters which we mentioned, which is not really necessary. The angle and then the radius. We need to add this line first of all. After that, now we are going to transform. So transform is a special command. So just 1 second. Spherical, cylindrical we need. So let us take one good example for that first of all. So let us transform radius, now we are going to say that radius is all radius. We have already defined the keyword radius. Suppose by r we define the radius. Now suppose the angle we denote by the variable name theta. So we are defining the variable name and we are mapping it. Height we denote by using z. Okay. Now we are going to plot. So remember that. So we are going to transform, and if we ask for theta, then we need to define the theta. Sorry, I need to define all these variables. Variable r, theta, z. So now onwards, the coordinates. If I use the variables r, theta, if I use the triple r, theta, z, it will actually stand for the cylindrical coordinates r, theta, z. Okay, that's what essentially I am going to get. So it will be converted actually into r cos theta, r sin theta, and z, because we know that given theta, the cylindrical coordinates are nothing but r cos theta, r sin theta, and z. So we defined, we already defined that whenever we are going to use the radius parameter, that's denoted by the variable r. Therefore, automatically it's transformed into r cos theta, r sin theta, and z. So now, how to use this? So to plot this, what we have to simply do is we need to just define the function in terms of r. Then we need to define the ranges of r as well as theta. We need to define a function in terms of r, theta, and z. Then define the since it is plot 3D, we have to define only two variables. R and theta is enough. Now let us try to give r square. Plot 3D r square. Remember that r is now a cylindrical coordinate. We define it like that. R square, where r is in the range, say 0 to r, 0 to 3. Radius we are taking to be 0 to 3. Now suppose the angle we are giving from 0 to pi by 2, and z is not required, and the transformation now we need to say that which transformation we are using. That's a T transformation which is cylindrical. Okay, take documentation example. Now, if we keep the radius to be, if we take the function to be a constant, what will happen? Let us see. So all of the parameters with plot 3D will work even here. Suppose we take, this is just r. So r is in 0, 3. So we are supposed to, in every angle, we are supposed to distribute this r along. Now, if we take just equal to 1, then it's this. So which are the parameters that we have specified? Height we have specified. So the height is compulsory, and what we said is that in the plot, the two things are not actually necessary. This theta and r. Suppose now, okay, let us just slightly modify it. So the transform command. Let us see what exactly the cylindrical is. So the cylindrical is supposed to be used only with plot 3D, where the position is specified by us. So we are constructing T is equal to cylindrical by that particular line command we are actually constructing. So these two variables are independent. When we are constructing in this coordinate system, two variables depend on, because we have in the case of f of xy, in the case of plot 3D, remember that we are plotting the function f of xy, therefore z is actually a function of x and y. Therefore, one variable is dependent and the other variables are independent. X and y are independent. X and y can be anything. So by this command, what we are defining here is that our function is by this line. We are defining that the height is this radius, and these two are independent variables. Therefore, we will be varying this. Height we are not varying. You can see from the example here. Here we are varying r and theta. Therefore, whatever we are giving here, we are not supposed to vary, and height is equal to a function of azimuth and radius. That's what the meaning of this is. If you change this, you will be getting different plots. So if you change this this construct, this cylindrical instead of that, if you modify this to suppose radius is independent and height and azimuth you are keeping as radius is dependent and height and azimuth are independent, you will be getting a different picture. Let us see that. So this is here. Now suppose we use r theta z. Suppose we use the radius here and height here. So then we cannot change this radius. Radius is a dependent variable. So let us use height. Therefore the function is 1. Radius is 1. Okay. Oh, I have used both the same thing. Radius, height, maybe in the same order I need to specify. Okay, let me just see. Height, radius. Radius equal to r, azimuth equal to theta. So radius, height, what was the thing previously? Height, azimuth, radius. But instead of that, height is equal to this, theta is equal to this, and transformation is t. So what is happening here? Name height is not defined. Oh, sorry. Theta is what? Got it. What theta is already here. So what is this then? So what were the three parameters? Height is defined to be z. Okay. Height is defined as z. Say that these two pictures are different, R03 and here we have Z03. So the height is varying from 0 to 3. And here we have radius is varying. So height is a dependent function. Z depends on, therefore the function is of the form Z equal to R theta. Function looks like Z equal to R theta. That you can see from this print. Let's use show to see what exactly the function looks like. Maybe we can try to use height in terms of azimuth and radius. That's the cylindrical system T is. But if you print T here, radius in terms of height and azimuth. So remember that we are supposed to use it only along with plot 3D, because plot 3D actually demands one to be a dependent variable of the other two independent variables. That's why we are using it like this. So in a similar way, we can define spherical coordinates as well. So just like this, we can define spherical coordinates. For that, what you have to do is we have to define spherical coordinates, and in that case, we have two angles and one radius. Radius, azimuth, and inclination. These are the three things that we are supposed to provide. So when we need, let me copy this. So theta and phi, let us call spherical. Radius, azimuth, and we usually call it as inclination. So we need to define inclination as phi. Sorry, 5. Maybe we can ask for 0 to pi by 2. Spherical, spelling is wrong. Sorry. This is what we get from here. Oh, sorry, I have not started. I have not, I think, opened a Google document. I just, okay, at least for the time being, I will just copy and paste. Just 1 second. So is it possible to find the intersecting point? What do you mean by finding the intersecting point? Intersecting point of what? So there is a question in the chat box. Is it possible to find intersecting point? I didn't understand what exactly you mean by the intersecting point. But for finding the intersecting point, essentially you are supposed to solve two functions, right? So if you want to solve two functions, then plot 3D is not going to anyway help, because plot 3D is supposed to be a tool only for plotting. So after that, you are supposed to use your techniques for solving the polynomial functions, etc. Plot 3D cannot by default plot any intersecting points, but what we have to do is we have to solve it for intersecting points, the functions we have to solve. Then we need to plot what do you call those points. For example, suppose that we have a plane as well as a plane as well as a surface. So to find the intersecting points, what you need to do is you need to find out the intersecting points using the algebraic tools that we have already discussed. Then you need to plot those points. That's your DB. Otherwise, I don't really see that intersecting points. There is no default command as such. Okay, so this is all about plotting in different coordinate systems. Now let us try to see. Okay, that parametric plotting is what I wanted to say after this. This is a kind of a transformation, but on the other hand, there is another direct plotting as well, like cylindrical plot 3D, spherical plot. Such kinds of things are also there, but these are all in some way under the hood. They are all using the plot 3D function directly. So they are not directly coded, but they actually use the plot 3D function, and they are using that function. Now, with the plot 3D function, there is an extra parameter that we can specify, which actually gives, if you have a very resource hungry function, and if you want to plot that function, then you can reduce the number of points. Remember that plotting always happens using some sample points. Okay. So plotting is done using sample points, and therefore if it's a complex function, the sample points required is also going to be much high. Therefore that system may sometimes hang. Therefore, if you have a very complex plot, if you have a very complex function to plot, which is your undefined or defined in some other way, then probably you should reduce the plot points to see Sage working much more efficiently. Let's say the sphere, not sphere, paraboloid. Or sine of, to see it more visibly. Okay, sin x square plus y square. But doesn't seem to give much effect here. It seems to be not that smooth now, because the plot points used are much less. So if you use less points, what happens is that smoothness of the curve will decrease, because it's trying to make a continuous curve using less number of points. If you use less number of points, if you calculate less number of points on the three-dimensional space and try to plot, that is not going to give a smooth plot. So plot points is one command that we can use for making the code a little bit more efficient. But of course, at the sake of losing the smoothness of the curve, you will not get a smooth curve if you use less number of points. And we can also specify that in the y direction use less number of points, x direction use less number of points. That also we can specify by using an ordered pair like this. Suppose that we define x direction 10 points and y direction 100 points. So the smoothness will be there. So the smoothness will be lost in the x direction more. But in the y direction will be smooth, much more smooth. This is also possible. So a lot of commands are there associated with the plot 3D itself, and you can see a lot of options like applying transformation, and even applying transformation itself there are several other transformations, and that itself is consists of the documentation consists of several pages if you try to read across that thing. So spherical, so in addition to that, spherical plot 3D is there, cylindrical plot 3D is there, in addition to using plot 3D and applying the transformation. That is also quite possible. All these commands, as I told, that mainly depends on it finally comes down to using this what you call plot 3D itself. Now let us see some parametric plotting as well. So parametric plotting in the sense that suppose that we have three components. We are trying to plot in 3D, but the components are specified in terms of a single parameter. Okay. For that we use the parametric plotting. For example, suppose that we define parametric plot 3D. Suppose we define u as a variable and try to use parametric plot. We can the plotting will take place depending on the single parameter u, but it will be 3-dimensional. For example, something like this. So using parametric plot. So let us define the usual variable t or u. Just like parametric plot, we have a parametric plot 3D option available. Sin u, cos u, and say 3-dimension, say u. Keep it in a tuple, and after that just specify the range of u. So this is a curve. This is spiral. On the other hand, if you use the height to be u, you will be getting just a circle at height 1. Because sin u cos u actually gives you circle, and the height is 1. Therefore, when u ranges from 0 to 10, different values of sin u cos u is taken, but everything is plotted to the one height. So we are getting a circle. So this is a curve. Okay, parametric plot 3D actually gives a curve, not a surface but curve. Of course, if you define 2 parameters, what will happen? Suppose that you specify 2 parameters, sin u and cos v. If there is only one parameter, you are going to get just a curve, sin u, cos v. U is in 0, 10, and say v is also in 0, 10. And if you take this to be v instead and this to be u, see that sin u cos v is corresponding to every v, every u, sin u cos u is constructed. Sin u cos u means that for v is equal to 0, sin u cos u is, so this is not actually necessary. If you go up to pi by 2, let's see up to pi by 2 and see what's happening. You will get only up to this pi. So half the cylinder in this way. But this is not necessary. This pi is good enough. So even pi is not required because it's going up to height. So if you take 1, what will happen is it will go only up to, the height is defined by this v. So just as in the previous case, we can enable mesh and all other such kinds of things, whatever is required, and color maps we can apply. And there is another parametric surface called the Mobius strip, which is usually useful in the case of higher mathematics. So that we need to import from plot 3D. We can see several things, several parametric surfaces available by default. So parametric surfaces available by default, if you want to see from sage.plot 3D surface, import star. So what are the things available? It gives Mobius strip. It gives probably several other things. Mobius strip is just one. So that's the problem. Even from the documentation, it's not very clear that what are actually the things available unless you get a very good documentation. But now the Mobius strip itself is available is one very famous example in the parametric surface. So the Mobius strip is already imported. Therefore, let us use MOEBIUS strip. Within that's a parametric thing. So the parameters required, there are 2 parameters required. So if you use 2 parameters, then suppose we give in 1, 2 some way. This is the Mobius strip. Suppose now we give 5, 5. You actually get a strip kind of thing. So it uses 2 parameters, x and y, or u and v. So the definition of Mobius strip, how it's defined is, it's not very clear to us, but what we can say is that there is an internal definition of Mobius strip in Sage, and therefore we can straight away use it, and only 2 parameters are required to be specified. Even if you specified much more higher value, that's not actually going to make much sense, because Mobius strip it's a finite thing. Therefore, even if we specify it to be 25, what will happen? So if you just, okay, its width increases. So if you just give 1, okay, this is standard thing that we usually see. So this is the standard Mobius strip that we usually observe. And as previously, we can specify the CM color map. Color maps HSV probably we can give. Let us try. And let us give the color to be, as per the documentation it works, color to be, so define C XY itself, because XY is already a, so okay, hopefully it will take X and Y, C XY as the parameters, XY equal to, or sorry, return x square plus y square. If you say the color CM, if you give, then how do this look? Oh, it looks like a red color thing. Square plus y square, or maybe sine of that to make it varying a little bit. To make it a little bit colorful. So what type of color is what type of function? If you use for CXY, you get a beautiful looking plot is not very clear. The only thing is that we need to just use the documentation, use some function so that randomly only we are trying, of course. That's not actually a very good thing, trying something randomly to get something. But unfortunately, as I told, the documentation, so you need to actually go inside the code of Sage Mathematics. But of course, that is also possible because the SageMath is an open source software. You can of course find out the code inside that, and you can find out what exactly the things that you can read and understand if you are a little bit good in already done something in programming. So of course you have been doing some kind of programming even now. Therefore, from that you can probably understand that what are the things that that is confusing to you from the document. Not if not from the documentation, then from the code itself. That's your living. So now let us go to the parametric plot. Parametric plot we have already discussed. Now let us go to something called vector field plotting. So vector field, we know that. So we specify some vectors, and so the vector is actually, as per the definition, the vector is constructed from the origin 0, 0 to the point. Okay, but in the vector field case, what happens is that vector is now translated parallel to the original vector to the point where we are specifying. For example, suppose that we want to plot 1, 0, 0. In the vector field, 1, 0, 0 will be initially drawn from 0 to the point 1, 0, 0. After that, it is placed, moved parallelly and placed with its initial point at 1, 0, 0. Okay, that's what's happening when we plot vector field. So for plotting vector field, we need to just use the plot vector field 3D command. Let's define 3 variables. Plot vector field 3D. So if we specify the vector to be just 1, 0, 0 for x, y, z in some specific range, x 0, 1, y 0, 1, z 0, 1. So what's happening is we have just placed 1, 0, 0 vector at all the points in the range x from 0 to 1, y from 0 to 1, z from 0 to 1. So 1, 0, 0 is the vector placed everywhere. We are not at all placing any other vector anywhere else. So 1, 0, 0 is the vector that we are plotting, placing everywhere. So now that's a constant vector. That's why it's appearing like this. It's appearing like this. That's why. Now, on the other hand, suppose that we use plot vector field 3D sin x cos y So we have already specified x, y, and x is already given here. What's the problem here? Sin x, cos y, and suppose we put z, what will happen? What's the issue here? Plot 3D 1 0 zeros, x 0 1, probably it's a zero length vector. I don't know why it's happening like that. It's because of the what you call the function definition, I guess. Let me just change that function definition. Okay, then let me use an example from 2x y square z cube. I'm just randomly trying with something. Sorry, 2x is wrong. 2 star x because of the function, I guess. So this is actually giving some good output. So it's not actually see that the length of the vector is also increasing because x and y, xy is depending upon that z cube. Okay, if I give z in the range 1 to 2 z cube, I should get something bigger. Okay, how do I get circular vectors? Suppose that I want sine x and cos y and 1, but I think I already tried that. Sine x, cos y, and say just 1. No, that's not happening somehow. I don't know what the reason for that is, because the function is not probably good for plotting in plot 3D. Okay, so that's about parametric vector field plotting. This can be achieved like this. Now one more important thing that I wanted to mention today itself is just like the implicit plot, there is an implicit plot 3D function as well available. Okay, so we have seen that previously we for plotting the planes like x equal to 1, it's actually difficult because plotting plot fxy, it actually looks for z equal to, z is always the dependent variable and x and y are independent variables, but we have seen that using the rotate we can achieve that, or using the transformation we can somehow achieve that thing. But now instead of that, implicit plot can be actually helpful in doing that. Implicit plot. So implicit plot, just like implicit plot, the command structure is exactly the same. So x square plus y square equal to 1, say. So this essentially means that for every z height you are supposed to keep the circle. Therefore, it's going to be a cylinder. X in range 0, 1. This is not going to be a cylinder. Minus 1 range is required, half cylinder. Y in range 0, 1. Z in range 0, 1. Or if you take minus 1 to 1, you will get a cylinder like this. Now you can plot the plane as well using this. Plus, here it's not very difficult to x equal to 1, say, and define some opacity as well. If you do that, okay, if I want x equal to, I should have plotted x equal to 0. X equal to 0 is nothing but the yz plane. That's what I wanted. So we can get that plane also here. So implicit plot 3D is the way to get something like this. Now, if we want to plot level curves, what do you do? So suppose that you have a function f of xy. Suppose that f of xy is equal to so what do you mean by level curve? So f of xy, the surface is there. F of xy is equal to c is something that you want. Okay, for that what will you do? For f of xy is equal to c. For that you may have to use this implicit plot 3D itself. So plotting level curve. For example, suppose that we have x square plus y square, the cylinder. Now suppose that x square plus y square equal to 1, the cylinder. Now suppose that we want to plot x square plus y square equal to 1 just at height z equal to 1 or z equal to 0.5. We don't want anything else. So we basically want a circle at z equal to 0.5 on that cylinder. But for that, what you can do is you can do the implicit plot, but you need to use a small trick that if you use the implicit plot, the z range you need to make it very small. So like this. Okay, let me just take p equal to this. After that we will use show p plus equal to this. So I want a level curve at x square plus y square, level curve at z equal to 0.5, x square plus y square equal to 1 once again. But what I do is at 0.5 I need 0.5, 0.55. Make the color also a little bit different. Color equal to red. So essentially we are actually plotting something 3D. It's a curve with thickness, but the curve with thickness is really small so that we will not see the thickness anywhere. So the level curve is here. If you reduce this width, you may get something really small. So this is the way to plot level curves using implicit plot 3D. Okay, this is actually just a kind of trick. So as I told, the documentation of plot 3D in SageMath is very extensive, and you can virtually plot anything that we usually require in the case of plotting in 3 dimension in mathematics. But the thing is that the documentation is, as I told, it's extensive. Not only that, sometimes you may have to dig into the code or dig into the documentation or several websites for finding out what exactly, if you have some special need other than what is by default defined in the documentation, you may have to just look at the documentation thoroughly to find out what exactly is the way to achieve certain things. As we have already seen, certain commands can be confusing, but if you start using that, most probably you may not require all the commands, of course, because whenever we do some mathematics, we will need only very few number of commands for performing our own mathematical operations. Therefore, once you understand, once you try to get acquainted with the command structure, it will not be really that difficult. So with this, probably I will. I had initially said about doing something in graph theory. So maybe we will start tomorrow with graph theory, and then Laplace transforms also we will try. And the other problem we had previously is to define arbitrary group operations if possible. So Laplace transform, graph theory, Laplace transform, and the group related things we will try to do in tomorrow's last session probably. So definitely we'll start with graph theory. So that was the first thing that we wanted to discuss towards the end of today's session. But plot 3D was something really extensive, having too many things available for discussion. So that's why we spent some time on that. So if there are any questions related to this, I will try to answer today, or I will try to complete that answer tomorrow. So I'm stopping my words for today. Thank you.
Thank you very much, sir.
Excuse me, sir.
Yes, please.
Sir, which type of book we are used to give our lecture in front of the student that the lecture becomes understandable?
There are
For
there are for different topics. I think you need to actually look into different books. That's one problem. So one Sage for undergraduates, one book is already available. Sage for undergraduates. That's a book that actually tries to demonstrate few things. But if you that students can read it only with the help of you. I don't think that students can directly go into that book, but if you are helping the students, Stage for Undergraduates by, I think, Grigory Bard, Bard, I think that's the book name. Probably you can download that book from the internet. Now, if you want to do some calculus related to Sage, Sage Math Advice to Calculus kind of book is there. So let me just give you one. I have listed some of these books in my web page. I'll just give you the link of that. Just 1 second. Let me find out. Yeah, I have listed a few resources. So here you can find, I have listed some 3 books. You can find links to those books and you can probably download also.
yeah, thank you, sir.
So thank you, and tomorrow we will be, as I said, we will start with graph theory, then move to Laplace transform and some group theory part also, and we will probably conclude. So thank you very much once again.
Thank you, sir.